In the last video, we described how to recognize the stereochemistry of chiral centers based on how the molecule rotates polarized light as D versus L for rotating light counterclockwise, or L versus rotating light clockwise, R. We also learned the systematic way of assigning the configuration of chiral centers as R versus S using a defined set of rules to describe those. And here we will go ahead and apply that to classify our molecules as either raccoons or snakes. Okay, it's not really raccoons and snakes, but I liked the illustrations. Let's go ahead and take a look at some example problems. Before we begin the example problems, I am going to summarize the rules for assigning the configuration of RS chiral centers that we covered in the last video. I'll go ahead and screen capture that here so that we can use that toward determining the configuration of some unknown molecules. So here we have our rules for assigning R versus S to each chiral center within a molecule. Let's apply these rules that we learned about in the last unit toward an example problem. Here we go with our example problem. I am drawing in my tetrahedral carbon with two lines, a wedge pointed toward us, shown here, and a dash pointed away from us. At the ends of those lines, I'm going to fill in the different groups that are bonded here. We recognize that the carbon, which I have put a star on, is a chiral carbon because of the fact that that carbon has 4 different groups bonded to it. Keep in mind, an ethyl group is different than a methyl group. Even though they both have a carbon directly bonded to the chiral center, they are not the same group. One has a longer chain length than the other. So that constitutes 2 different groups here, and hence we have 4 different groups in total, making this a chiral center. Anytime we have a chiral center and we show our wedges and dashes, we can assign that chiral center as R or S. If we didn't show the wedges and dashes, that's still a chiral center right here, but it would be a chiral center where we don't know whether it is R or whether it is S. It would be undefined. So, looking at this particular structure here, we need to go through the rules here. First off, we're going to rank the groups that are bonded to the chiral center in order of atomic number, where number 1 is the atom that has the highest atomic number directly bonded to our chiral carbon. Number 4 is the lowest. Let's highlight the atoms that are directly bonded to the chiral carbon to get started on this step. Bromine, carbon, carbon, and hydrogen. I've highlighted in pink the atoms that are directly bonded to the chiral center. Now we ask ourselves, which of those has the highest atomic number? If we look at the periodic table, which I recommend you keep handy while doing these exercises, we will see that bromine has a higher atomic number than carbon, carbon, or hydrogen. Hence, bromine ranks number 1. In last place is the hydrogen atom on our dash here, so I'm going to put that as number 4. Hydrogen will always be last if there's a hydrogen present, because hydrogen is an atom with an atomic number of 1. That's as low as it goes. Now we have a little bit of challenge here because we have 2 carbon atoms. Our 2 carbon atoms here and here have the same atomic number. They're at that spot that's directly bonded to the chiral carbon. So that's where we follow this rule. The atoms directly bonded to the chiral carbon are identical, so move 1 position down the chain to the first spot that differs. So from our methyl group here, we had a carbon in first place, and then after the carbon, the next thing in line, I'm going to put in parentheses here, what's bonded to that particular carbon as our tiebreaker. Bonded to that particular carbon is 3 hydrogen atoms, so I'm going to put H, H, and H here because of these 3 hydrogen atoms. So this particular carbon, our tiebreaker opportunities are a hydrogen, a hydrogen, and a hydrogen because that's what that carbon is bonded to. On the other hand, up here, this particular carbon in red highlighter is what I put outside the parentheses. Then to keep myself organized inside the parentheses, I put what that carbon is directly bonded to. As we dissect this formula, this particular carbon going away from the chiral center would be directly bonded to one other carbon atom, that's the carbon of the methyl, and the two hydrogens here. If we drew this out as a Lewis structure, we see two hydrogens and a carbon directly bonded there. And so that's what I'm going to put here in these boxes is carbon, hydrogen, hydrogen, where what's shown in the boxes reflects what's directly bonded to that particular carbon atom that is under investigation. This carbon right here being directly bonded to one other carbon atom going away from the chiral center, that's the carbon right here, and bonded to two hydrogens, we put that in there. Now we compare what we see for this grouping relative to this and rank based on atomic number. As we saw before, our first spot is a tie, carbon versus carbon, and then when we go to the next spot, what we see is that we have a hydrogen here versus a carbon up here. Carbon has the higher atomic number of the two, and hence the carbon atom wins. Therefore, we would rank the ethyl group as number 2, because we already ranked bromine as number 1, the methyl group as number 3, and hydrogen as number 4. With that, we've ranked the 4 groups that are directly bonded to the chiral center. And we've used this addendum here that if the atoms directly bonded to the chiral center, such as the carbon of the methyl group and the carbon of the ethyl group, are identical, then we went down the chain one more spot. We put one more spot down the chain in parentheses here so that we can compare what was bonded to each of those positions, finding that the carbon atom that was one more spot down the chain has a higher atomic number than the hydrogens here of the methyl group. Hence, this ethyl group wins over the methyl group. So, therefore, we ranked that as number 2. We oriented the molecules so the lowest ranked group points away from us. For purposes of this introductory class, the lowest ranked group will be pointed away from you by default. So we have that squared away here, and then we're going to draw a circle to finish this off from the highest ranked group, number 1. Then we connect over to the second highest ranked group, number 2, and then finally to the third highest ranked group. Ignore that fourth group there. And we look at what direction our arrows go. To go from 1 to 2 to 3, we're going clockwise. And so we would describe this particular structure as having the R configuration. And we could actually come up with a complete Iupac name for this if we were asked to do so. We might be asked to do so, provide the Iupac name including the configuration as R or S. We would put the term R at the front end of the name either in parentheses or not. You've seen it both ways before, and a dash to start into the name, and then follow the Iupac rules like you normally would. Iupac rules say find the longest carbon chain, where that longest carbon chain will follow through what I'm showed in yellow here. That longest carbon chain has a grand total of 4 carbon atoms, methyl group 1, CH2, 2, this carbon 3, and that carbon number 4. So the parent name for this molecule would be filled in as butane, a 4-carbon chain. There's no ketone groups or alcohol groups here to give it butanone or butanol or anything like that. So following this chain, and the way that we're going to number this chain is so that we put a branch as close to the end as possible. Looking at this structure, the only branch we have is this bromine branch, and so numbering from this end with the CH3 as carbon number 1, and this spot is number 2, 3, 4. Number 2 is where we see the bromine. So we would call this R2-bromobutane. And now we've created a name that indicates the configuration of the molecule so that we will know, even if we haven't drawn this structure out or have a molecular model handy, exactly how the atoms will be oriented in 3-dimensional space by attaching this designation of R to the molecule. Let's do another example problem. In this example, we're going to take a look at lactic acid. Lactic acid is interesting because one of the enantiomers, the S enantiomer to be specific, is produced during strenuous anaerobic exercise, whereas the R enantiomer is what gives sour cream its distinct sour flavor. So, taking a look at this structure, we need to be able to determine whether this is the S form, produced during strenuous exercise, or the R form that has a very different function as giving the flavor of sour cream. Which one are we dealing with here? Well, first things first, we need to find the chiral center so that we know what we are working with regard to assigning R versus S. Chiral center is right here. We've recognized this as a chiral center because this carbon is directly bonded to a hydroxy group, directly bonded to a carboxylic acid group, directly bonded to a methyl group, and what's not shown there is, in a line angle formula, the hydrogen atom is implied. That hydrogen atom I could put to the left, to the right, wherever I want. It's the lowest ranked group, so it doesn't matter where it goes, except that it does need to be recognized that it's on a dash there. And if you were solving this problem, you wouldn't necessarily even need to draw that in, but I like to draw it in to remind myself that this is a chiral carbon, and I'm not leading myself astray by erroneously pointing that out as a chiral carbon. It does indeed have 4 groups bonded there. Now, ranking those 4 groups, hydrogen ranks the lowest because that has the lowest atomic number. And now thinking about ranking the other groups, 1 through 3, we have an oxygen directly bonded to our chiral carbon. We have a carbon over here of the methyl group directly bonded to the chiral carbon. And we have a carbon over here that is part of the carboxylic acid group. So thinking about how we'd rank those as 1, 2, and 3, the highest ranked of those is going to be the oxygen, because if we look at the periodic table, oxygen has a higher atomic number than carbon. So that's going to be ranked as number 1. Now we have a tie to break because we have a carbon atom here, and we also have a carbon atom over here. Now how we break the tie is we ask what each of those carbon atoms is bonded to. I'm going to put that in parentheses here to indicate what each of those carbon atoms is bonded to. The methyl group carbon is the end of the line, so it is just directly bonded to 3 hydrogens going on down the chain, so I'm going to put hydrogen, hydrogen, hydrogen. The carboxylic acid group, on the other hand, we fill that in as being directly bonded to 3 oxygens. How did I come up with 3 oxygens and not 2? Your eyes are not deceiving you. The pi bond here counts as a second oxygen. So hence oxygen, oxygen, oxygen. So we have something to fill into all 3 of those spots. And so comparing a methyl group to a carboxylic acid group is going to definitely be the winner because in both cases there's a carbon atom, but in one case the carbon's bonded to hydrogens, in the other it's bonded to 3 oxygen atoms. Oxygen has a higher atomic number, so oxygen is going to go for the win. So we'll fill that in as number 2. Methyl group is number 3. And the molecule is oriented so the lowest ranked group points away from us on a dash. That's our hydrogen. Now we're going to go into step 3 of our system here. Draw a circle from 1 to 2 to 3. I'm going to go ahead and draw that in here for us. Going from 1 to 2 to 3 takes us in a counterclockwise direction. And so we would describe this as S-lactic acid. And so S-lactic acid is indeed the enantiomer that's produced during strenuous anaerobic exercise. And so if you're having some delayed onset muscle soreness today, you may have an accumulation of this particular stereoisomer of lactic acid present. Now let's take a look at one additional example problem in the upper right corner. I encourage you to hit pause, try this on your own, and then press play to see if you are able to do this. Let's take a look. Finding the chiral carbon in the molecule, I put a star right here because it's this carbon where there are 4 different groups bonded. There's the methyl group, the CH2, and then followed by the aldehyde. Remember the abbreviation for an aldehyde group is CHO. So when we see that CHO there, what we need to remember is that that's really a carbonyl directly bonded to a hydrogen. And then coming this way, we have a CH2OH group. And the hydrogen atom would be on a dash to fill in the final piece of the tetrahedron. That is not shown. I'm going to go ahead and sketch that in just as a reminder. And I can put that literally anywhere. I'm just putting it here off to the right here. But that dash you could put down here, wherever you want to put it. I just like to fill it in as my reminder that there is a hydrogen atom there. So now ranking the 4 groups, I'm going to go ahead and fill in what is hopefully the easy part first here, that number 4 is our hydrogen. That has the lowest atomic number, so that's going to be ranked lowest. Then we need to deal with the 3 groups here, here, and here that each have a carbon atom as the first atom going away from the chiral center. So there's a carbon atom here, a carbon atom here, and a carbon atom here. So how do we deal with that? Since it's a tie, what we do is we go ahead and we look at the next atom in the chain to find the first place that differs, where we still look at the atomic number of the particular atom as our way of differentiating them. So taking a look from here, this particular carbon atom right here that I've got in red down here, we ask what it is directly bonded to as we go away from the chiral center. I'm going to put those into parentheses. So this carbon atom is directly bonded to 2 hydrogens, and it's directly bonded to the carbon atom right here. So I'm going to put into my parentheses carbon because it's directly bonded to 1 other carbon, hydrogen, and hydrogen because it's also directly bonded to 2 hydrogens. So coming from this carbon is directly bonded to another carbon, and it's directly bonded to 2 hydrogens here and here. Similarly, I come over to the left. I'm going to put in parentheses here what 3 atoms this carbon right here, this is our carbon atom, is directly bonded to. It is directly bonded going away from the chiral center to an oxygen here, and it's a CH2, so it's directly bonded to 2 hydrogens. Therefore, into my parentheses, I put the oxygen and the 2 hydrogen atoms just to keep myself organized about what is this carbon directly bonded to. That carbon is the one outside the parentheses. Inside the parentheses is everything that particular carbon atom is directly bonded to as we go away from the chiral center, oxygen, and then the 2 hydrogens that are directly bonded there to that CH2 group. Finally, we come up here. This particular carbon atom is a methyl group, CH3, so this carbon outside the parentheses is the end of the chain. It's directly bonded to just 3 hydrogen atoms. So I'm going to put C and then H, H, H to indicate what it is directly bonded to. Now, with that in place, what we do is compare what we have in the parentheses here versus here versus here in my yellow highlighter as our tiebreaker. Taking a look at each, we have highest ranked atom here is a carbon, highest ranked atom here is an oxygen, highest ranked atom here is a hydrogen. Of those, oxygen has a higher atomic number than carbon, carbon has a higher atomic number than hydrogen, and therefore what breaks the tie is this oxygen atom here outranking the carbon atom here, outranking the hydrogen, and therefore we can plug in this as number 1, this as number 2, number 3 is our methyl group, and then to go about assigning this as R versus S, our lowest ranked group is indeed pointed away from us. So we are good to go on that aspect of things. Now what we do is we go from number 1 to number 2, and then number 2 to number 3 in order. So in order, we're going 1 to 2, 2 to 3. That is taking us counterclockwise, as we can see here. And so therefore, we would describe this molecule as having the S configuration. And if we were asked to provide the entire Iupac name of this molecule, we could definitely do that based on what we know about nomenclature. Based on what we know about nomenclature, we learned in the last unit that aldehyde groups rank higher than alcohols when determining how to name molecules. And so in finding our longest carbon chain, what we would do here in finding our longest carbon chain is we would go ahead and we would start numbering our longest carbon chain at the aldehyde group here. We would come through the molecule, starting from the aldehyde group, and calling the aldehyde group position number 1 of our longest carbon chain. Call that aldehyde number 1. Number 2 is our CH2. Number 3 here, 4 here, finding our longest carbon chain, 1, 2, 3, 4. My numbering is in gray for determining the Iupac name. Iupac name numbering is in gray. So 4 carbons in our longest carbon chain makes the parent name butanal, since there is an aldehyde group in that longest carbon chain. No need to call this 1-butanal, since it's implied that the aldehyde group must be at carbon number 1. And then from there, we look at what branches we have coming off of that longest carbon chain. At position 3 here of our longest carbon chain, we have a methyl group, and at position number 4, we have an alcohol group, or a hydroxy group as we can call it when it's a branch. So we would refer to this as 4-hydroxy 3-methyl butanal. So 4-hydroxy, I'm running low on space, 3-methyl, and the word methyl should run directly into the word butanal, and then at the beginning of that, put the letter S to indicate what enantiomer we are working with here. So S, 4-hydroxy, 3-methyl butanal would be the complete Iupac name for this molecule, where after we determined whether it was R or S, we went in and used our Iupac rules to find the longest carbon chain and number from the end, starting closest to the parent name designator, and specify the locations of the branches in alphabetical order here, hydroxy before methyl, and indicated the numerical locations of each to finish off this problem.